All right. Hi. Happy Tuesday. Thank you for being here. I normally have like a document of here's what we're doing today, but I ran out of time. Um, and that's also why you haven't gotten an announcement of like here's what we're doing this week. It's been busy. Um, so my plan overall today is we're going to do a quick review of what we talked about last time, of stacks and queues. Then I'm going to show you what it looks like to implement a stack with a linked list underlying data structure. I'll give you maybe 5-10 minutes to work together and see if you can do that with an array list for a stack. We I'll judge the time then and see where we're at. Um, we might do the same thing for queues. We might do a linked list version of queues together. And then we're into lab 7. So we're a little bit behind in terms of topics that we need to cover in this class. That's the hard thing about this class, where it's like a data structures and object oriented and a little bit of algorithms. So there's a lot that we need to cover. So I'm hoping that maybe by 4:30 or so we can start lab 7 and give you some time in class to work on it. And then the rest of that will be assigned as homework. Um, and that way that puts us on track to start recursion next class. I will say, make sure that you're coming to class on Thursday. If you can't, make sure that you set aside time to watch the video, because recursion is notoriously difficult. So make sure that you are coming and paying attention, because we're going to talk about some really important topics that you need to know going forward, and they're also very difficult. Okay, so let's do a quick review. So we're talking about data structures. In particular, we're talking about stacks and queues, which are different ways of storing some information. Both of these are linear, as in the data is more or less stored in a straight line. And a stack is a structure that only allows two main operations. So we've got these kind of walls, and we can only access the thing at the very top of the stack. And so our operations are, we can push, so add something to the stack, or we can pop, which is remove something from the stack. And at every point, we can only access the thing at the top. So we can't drill a hole in the side and grab something out of there. We can only access the top. So keep that in mind. So we talked about how it's used as a call stack. So like this is how we have been, this is how the compiler maintains the flow of the program. So once we call a method, that method gets added to the call stack. Once that method finishes, it gets popped. If something happens in between, if there's an exception or an error, then the program has to crash, and then it looks at the call stack, and if there's still things on the stack, then it says, hey, I didn't finish everything. Something went wrong. And it tries to give you information about here's what went wrong in there. But if we get to a point where the call stack is empty, then we're done and everything went well. Yeah,
That why it's called like stack tracer.
exactly. Yeah. Yeah. So when we have the option to like print the stack trace on an exception, that's what we're doing. We're saying, here's all the information I have about what called me and where, and leaves it to the programmer to figure it out. So then we talked about queues, which are basically just lines at their most simple, where you have the option, the two operations here are to enqueue, which is get added to the line, or dequeue, which is get removed from the line. So enqueue, you join. This is like if you're at the grocery store, when you enqueue, then you are joining behind the last person in line. And then when you dequeue, it's, oh, the person in front of you has gone and it's time for you to go and pay for your groceries. So you get DQ'd. We talked about what they're used for. Okay, and so then we made interfaces for these. So go over here. Let me move this down a little bit. So we've got our interfaces for stacks and queues. Both of these interfaces are just so that we can have common method names and return types. So however we implement a stack and a queue, we're going to have it hold some type of data. So that's those angle brackets with a capital T. And then we want the adding method, the adding operation, to be called push. That's what we want it to be called. And we want the removing operation to be called pop and to return that data that we removed. We also have peek, and then our is empty, make empty, toString equals, those kind of helper things. So we did that for stack, and then we've got the same sort of thing for queue, where the two that we really care about are enqueue and dequeue. Where enqueue adds something to the back of the queue, dequeue removes something from the front of the queue. I will note, be careful how you spell dequeue, because let me see if I can spell this correct. So there's something called a DEQUE, and that is pronounced it's pronounced deck, and that just means it's a double-ended queue. A double-ended queue is something where, so let's say a normal queue is we add to the back and remove from the front. A double-ended queue is where we can both add to the back and remove from the back, and both remove from the front and add to the front. So so there's still this process of moving forward in line where we still have the NQ and DQ, but there's the notion of someone could cut in front and like maybe have higher priority, so they need to get served first, or someone at the back of the line can realize, oh no, I don't want to sit in this, and so only the person at the back can leave. Or maybe if we're at the store, management comes over and is like, oh, you got to serve this person first. So this is a deck, and that's something different. So the DEQUE, nope, that's not how you spell it. DEQUEUE, DQ, that's the operation. That's this operation, where we're removing something from the front of the queue. Okay. So we're gonna, I think in the interest of time, I'm just gonna show you how the push and pop work for the linked list stack. So using the LL code that we've got, how does that work? And so remember last time we talked about how we kind of took this stack. So if we look at it upright like this, when we're implementing it with a linked list, to visualize it, maybe we just kind of set it on its side so that it looks like this, where we've got the head of the list is going to be the top of the stack. So head of list equals top of stack. And that's the really important thing to remember. So if we know conceptually how a linked list works, then we can just translate all of this information because we know how, we know how to insert and delete things from a linked list. And so when we're working with a stack, we just insert and remove at the head. Because for a stack, we only care about the top element. That's just what we can remove or add something new. So that's what we need to focus on, is just removing at that index 0. And keep in mind that the top of the stack is the head of the list. Okay, so I believe we started this last time. And so I want to just do push and pop. And these are going to be super simple. So to remind ourselves, we've got a field for our stack, and that field is just the linked list. So that's our underlying structure. And we may want to make a note for ourselves that the head of list is top of stack. Just to remind ourselves, this is our fundamental assumption. This is how our data is structured. So we've got that. And we've got our constructors to set everything up. And so to push something onto the stack is to just add something to the top. And when we add something to the top, we're adding something to the head of the list, which is just at position 0. So push is super easy once we have all the linked list implementation, where we say list.insert, since that's a method that we have, at position 0, and we want to give it that parameter, the data that we want to insert. And that's it. So we just insert something at the beginning of the list. So for pop, so one of the things we need to make sure of for pop is that if, in case we have an empty stack, we don't want to like let something happen if someone tries to pop from an empty stack. So maybe we check if this is, or I would normally call the is empty. But since we don't have that, I will refer to the list that is empty. So if the list is empty, let's see if no set element exception will work. Probably have to import it. So if we try and pop from an empty stack, then we need to say, no, not allowed. So we can throw an exception. Otherwise, now we proceed, where we remove the thing from the list and then we return it. So we've got a method get head, or we've got get given an index. And so let's think. So we want to get the actual data there. So I think we just use the get because that returns type T. The data, we assume that the data is of type T at this point. So I'm going to call get at position 0 because for a linked list, for a stack, all we're concerned about is the head of the list. So position 0 is really all that we care about. So first we get that data, and now we have to remove it and return it. So to remove it, we say list.delete that thing, and then we just return that data. So we get the data, we delete it, and then we return it. And so we're going over these operations just because it's important for us to kind of understand how stacks work and how they're implemented. Because later on, as you progress in the computer science classes you take, you kind of take stacks for granted. So we're looking, here's how they work, here's what operations they have. Okay, so without typing anything, if these are our main operations for pop, if so peek is the operation that returns the thing at the top of the stack but doesn't remove it. So how would this change for peek?
Could we just take out the
Yeah, so keep lines 34 and 36, but just don't delete it. So I can copy that and just type val. There we go. Okay, any questions so far? All right, should be fairly straightforward. So in the interest of time, I'm going to leave these guys. And I would now like you to turn to your neighbor and first of all, so this was with a linked list. Now I want to do it based on an array or an array list. I maybe recommend array list because with arrays, you run into the problem of reallocating where we get to a point where, oops, we're out of space, reallocate. So I would maybe recommend using an array list as your basis instead. But talk with your neighbor, maybe draw some pictures. First of all, how do we translate a stack into something that works in this array structure? Where should the top of the stack go? And then how do you do those two operations, push and pop? Okay, so first turn with your neighbors and turn to your neighbors and talk about this for a minute. You can. I would maybe call it, so I think we're in the stacks package. And so we have a LL stack. So depending if you're planning to use an array or an array list, I would call it either array stack or AL stack. AL standing for array list. So I'll say, so we did LL stack, which we based it on a linked list. So depending on whether you choose to use just a normal array or an array list, create one of these classes. Yes, because the stack interface, yeah, so make sure it implements our stack interface. Where'd my mouse go? Make sure it implements this interface, just because that gives us the method names. Maybe let's come to a consensus before we do the coding. Where's the top of the stack? What is the error?
Is the type array was stack must implement the inner structure that the stack to push to.
So what does that tell you? While you think about that. Where's the top of the stack?
Yeah.
Okay. Analogous to what we did in linked list. That's a fair assumption. How do we do push and pop? Yeah, if you want to go.
Set the zero element to whatever you want, move first, and then move everything on the next over.
Mm-hmm. So that's what's happening under the hood. Where we have this idea, and so so the step would be to first push everything over and then set the new element to be there. And that's kind of like, if your like closet is full of clothes and you want to put something like at the leftmost, first you gotta shove everything over and make room, and then put your new hanger there. Yeah, so if you use an array, then you have to do that manually. If you use an array list, there should be, I believe it's insert similarly is what it calls, and it does that for you. Okay, so that's push. What about pop? You or anyone else who has an idea? How do we,
On the way to this, you could just call it move, right?
I think so, yeah. Um, okay, so this is the documentation for array list. This tells us here's all the operations we can use. So if we go through and we look for something that looks like what we want, so maybe add could work if it inserts the specified element at the specified position. Get, remove. So yeah, so remove probably works. Yeah, so I think, do we have an insert? I don't see an insert. So I think it would probably need to be add. So this is something because if you're using different structures, the names could be different. So make sure if you're using, especially like something that Java came up with, just check the documentation. So that way you can see, here's all the options that I have and try and match what is available to what you're trying to do. Okay, so we're almost to the coding part. Okay, so instead of insert, we're at add, and we give it some index, which if we have the top at the beginning, that'll be 0, and then some data. And then for pop, it's similar, remove. Okay, so your job, creates one of these two classes. I would like the field to be that structure. I would like a 0 parameter constructor. So that's going to be similar to what we had over in LL stack, which is this guy. So just instead of LL, it uses a different data structure. And then I want the NQ and DQ methods. What does that look like in terms of these operations, which we've talked about? Okay, so go ahead and do that. Talk with your neighbors again as needed, and I'll go walk around. Okay, let's come back together and do this. Okay, so I'm going to make a new class. And this class will live in my stacks package. I will call it AL stack. And it will hold some type of thing. So I'll give it the angle bracket T. And it will have an interface. The interface is my stack. And then I checked, take my inherited abstract methods, just so I don't have to type them all over again. And a finish. Cool. So I've got my basic class set up. I've got these abstract methods that are here ready for me to implement. And so we need to first declare, here's where I'm storing all this information. And so that lives in my field. So I'll call it list. You could call it whatever you want. I saw some people use capital L list or AL. I think that's fine. I'll just call it list. And I'm just declaring it. We're going to set it up in the constructor. So I just need to import that and we're good to go. So I do want a 0 parameter constructor. So public, no return type, AL stack, that's exactly the name of the class, which is exactly the name of the file. And so here I'm just initializing my list. So now we have the right-hand side of that declaration. So list equals new array list. And I can put type T if I want to right there, or I could just leave it blank and the compiler will infer that for me. And that's all I need to do to set this up. So to push the elements, I need list dots. Okay, so there's some different things in here than there were on the documentation. So there was, I think it might be an older version of Java on the documentation, probably. So not only is there add, which is what we initially planned on using, there's also add first or add last. So that makes it easy for if we had, for example, decided that the end of the list is the top of our stack. We could have made that assumption and gone forward with that. And so add last would be easy for that. So we could either do add 0x or we could just add first x. That kind of makes it easy for us. Let me type that up, 0x, and then I'll just comment that out. So equivalent ways of doing the same thing. And then for pop, what does someone want to tell me what their pop looks like? Yeah.
So mine's relatively the same compared to the linked list one. The only thing instead of like for list dot get 0,
Mhm.
I have it since my, I guess, pop is the back of the list.
Okay.
I have it as get list dot size.
Mm-hmm.
So it kind of gets like the size, kind of like the last element in linked list in the array list. Thinking that
Mm-hmm. Yeah. I think you can also do list dot get last. Yeah. So that's a handy shortcut. Again, they're equivalent, so. Or I think list dot size, you might need to do size -1.
Yeah, minus one.
Yeah, yeah. Since we start indexing at 0, it has to be size -1. So, or we could do list.get last. And that's still if the top is stored at the back. If we're assuming that it's stored at the front, we could say list.get first and store that value. Yeah, VAL or TMP, doesn't matter the variable name. And then what? We get the value, we need to remove it. How do we remove it? So I think we have the option as well of removing, if it's at the front of the list, we could remove index 0. Or if it's at the back of the list, we could remove index size -1. Or again, there's the handy first or
Just-
last.
Slash move one.
Yeah. I will note before I click on this, if you look, it says here's what return type it is. So the return type of remove first, it returns the remove element. So technically, because ArrayList handles that for us, we don't need to get that first element at all. We can just call remove and it'll return that for us. So because that's built into this remove method, we didn't have that in linked list. Yeah,
TMP instead of that for array.
just variable name.
So we can make TMP equals AL.remove first instead of AL.get first.
I'm gonna make it even simpler. So either we could do, so I'm gonna comment this out. We're gonna make it simpler as we go. We could say TMP equals list.remove first, and then we could return TMP.
It's even simpler than to just return list.remove first.
Exactly. So we could get that value and then return that, save it to a variable, or just don't have a variable at all and say list.remove first. Because remove first and let me move the comment down here, gives us the value removed. And so we just call that in the return statement. So if we do that, then, so this is all a process of let's make it simpler until we get here, the most simple we can do. So the only thing left is we need to check if list dot is empty, then again, throw new, what did I use? No such element. I'll just copy that line. Where we need to warn the user to don't pop from an empty stack. Okay, so that's pop. Peek is also probably really easy. That's list dot. If we're at the beginning, then get first. If we're at the end, then get last. Although we probably do need this exception as well. And there we go. Okay. Before we move on to queues, I just want to make a quick driver file to show you how we use stacks in practice. Stack demo, let's call it. And I will give it a main. So we've got our AL stack and we've got our LL stack. That's all good. Though I believe you'll have both of those options in the lab. So if you want to use one or the other. So to actually use them, we'll say, let's use the AL stack we just made. And I don't know, let's give it integers just to make it easy. Integer, I'll call it lowercase stack equals new AL stack, empty brackets, empty parentheses. Empty parentheses, that's calling our zero parameter constructor that we wrote. So we wrote what it looks like when we do this. And so now the only operations we can do, so here it shows all of these different operations, including some from object, the is empty and make empty we haven't implemented yet. But we've got peek, pop, and push. Those are ones that we implemented. So let's just, I want to push things and then pop things. So let's say, let's go 1 to 5 or 0 to 5.
Some reason. There's no public stack.
If you have an additional constructor, I think that's okay. You can just leave it. You can always have more constructors than you actually use. So, I++. And so I'm going to push each integer and then, oh, I actually do need the is empty. So I want to do, so here's the thing. So now that I've pushed things into my stack, I want to be able to pop things from my stack. And so in this case, since I know for sure that there's only 5 things in my stack, I could do this for loop again and pop them all. But I don't want to hard code that because there's always a possibility that maybe somewhere else, someone else has pushed something onto the stack. So here's a case where I want to use a while loop to say, while stack is not empty. And so the way that I say that is with the exclamation point and then using that is empty method. So since I haven't defined that, let's just do that really quick. That's going to be 1 line of code, which is just our stack is empty if and only if there's nothing in our list. And so we just say list dot is empty. So we just say whatever is in the list, if that's empty, then we don't have anything. If there's something there, then we still have something. Okay. So while that stack is not empty, let's just print out whatever we pop. So incidentally, if we push 0, actually, I want to make it 1 through 5. So if we push 1, 2, 3, 4, 5, my question to you is what are we going to get when we pop things? So if we push it in the order 1, 2, 3, 4, 5, will we get, let's take votes. Will we get 1, 2, 3, 4, 5 back? Or will we get 5, 4, 3, 2, 1? So, okay, we're gonna vote for 1, 2, 3, 4, 5. Who votes 1, 2, 3, 4, 5? Who votes 5, 4, 3, 2, 1? Cool. Let's see. Five, four, three, two, one. And this is because it's a first in, last out structure. So the first thing that we push, which is a 1, is going to be the last thing that comes out. So the very last thing we pop ends up being 1. So that's because of how we've set this up. Just to note, we cannot say something like stack dot remove, or like if we wanted to remove the 4th thing, we can't do that because that's not an operation that belongs to a stack. So this is something that I always see, so I just want to make this clear, is we can't like iterate through our stack. We can only say, is the stack empty? Yes or no. Either push something or pop something. Those are the only things we can do with the stack. When we're inside the data structure and working in here, maybe we can do something with indices and whatnot. But when we're outside and we're just dealing with the stack as a whole, the only thing the stack knows how to do is push, pop, and peek. And so this is going to be important for the lab,
Go to these,
the stack interface.
go to something. Oh, never mind. Go back. You can go back.
Okay. All right, we good? Okay, so now we've got an array-based stack. We've tested it out. So now let's do a linked list queue. So for this one, I'm going to, so if we had had more time, I would modify the LL class that we do have. And so that makes it so that we're not just going in one direction, but that we also go in 2 directions, but we just don't have time for that. So let me tell you what happens behind the scenes. So we're going to be using a doubly linked list, which means the arrows go both ways. So it's that, and we have, so with a linked list, we have a head, and with a doubly linked list, we also have a tail. So front and back of the list, which will help us as we do those 2 key operations of enqueuing and dequeuing. So having access to the head and the tail of this get first, get last. And so this makes it so that previously when we work with just a singly linked list, sometimes it means that when we iterate through that linked list, if we start at the head and then we have 5 million nodes, it's 5 million nodes long, that means we have to start here and go to the next one and go to the next one and go to the next one and go through all of those until we get to the last thing, right? And if we have 10 things in our list, not a big deal. If we have 1,000 or 10,000, then that gets to be a bigger deal. And so if we have set up the structure, so it's doubly linked, we can go both ways, and we have these fixed points of the head and the tail, that makes those operations really efficient. So it's really efficient to just add something else onto the tail, which is what we do with enqueue. And it's really efficient to just remove something from the head. Which say head points here now, and we remove the thing that's at the front of the list. The other thing I will note that happens behind the scenes when we transition is not only, so with a singly linked list, we can just like move the reference forward and remove any way to get there. And then we treat it as it's deleted, as if it's deleted. But with a doubly linked list, like let's say we wanted to remove this thing as the head, we also need to break that backwards link. So if each node has both a forward and backward link, then we need to set the previous pointer to be null. So that's what we have to do behind the scenes to say, no, really, you can't go back that way. Okay. So we've got our queue interface where we've got NQ and DQ. So let's make a class. I'll call it DLLQ. DLL stands for doubly linked list. And I'll add my interface. So if I type Q in the search box, one of them is the Java util queue and one of them is mine. So I want to choose the one that I wrote. The Java util queue probably isn't that different. But just, I want to use the code that I wrote. Okay. So now we get to this point, and from here, it's the same kind of process where the structure works a little bit differently, but we're still doing the same thing. So we want to have a way to store all this data, and the way we do that is with the underlying structure of the doubly linked list. And so the way we do that is with the java.util.linked list. It's implicitly a doubly linked list. So if we say right, so we declare it here, and then we just import it, java.linked list. And so if we hover over this, it tells us some information about this structure, which says that it's a doubly linked implementation, and it implements a lot of operations to do that for us. So we've got that. Now we just need our constructor. So I'll just have a 0 parameter one where we set up the list. And we instantiate it similarly to before, where the type name now is just linked list instead of array list, or linked list instead of LL. It's just a different type name. And I need the word new here. So now I have declared my field and I have instantiated my field in the constructor. And now I just want to say, what does it look like to NQ and DQ? So maybe, let's see, is there a way to easily go to, there is. Okay, so how did I get there? I hovered over this when I was declaring it. And then if your mouse is in here, there's a little icon saying open attached Java doc in a browser. And so that just takes you to the internet, where it says, and similarly, here's all our fields. Here's our constructor. And here's all of our methods. And so as we go through, we see add again, we see add first and add last. So we're probably going to say the same thing. There's get first and get last, and similarly. So it's the same methods as an array list, but it's just a linked list that's under the hood. So it's still this linear structure, but its underlying implementation is different. So we could make it an array list. I've just chosen to use a linked list. So this is a moment where I, as the designer, was like, I want to use the linked list for this. And the operations, the efficiency of operations in arrays versus linked lists can differ for the reasons that we talked about previously, where arrays, we can instantly index something, where for a linked list to get some index, we need to iterate through the list. And so in arrays, it's free. In linked list, it costs something. And similarly, we talked about for like if we were using an array, if we wanted to remove something from the front, then we need to shift everything over. Or if we want to add something to the front, we have to shift everything over and then add the new thing there. That costs something. We don't see that necessarily, but it does cost something. And in linked list, if we want to add something to the front or the back, then it's free. So there's trade-offs depending on which structure we want to use. That's the takeaway. That's why we study linked lists, to show that so we're starting to get into operations and efficiency, and some things are free in one data structure, but they cost something in another. So it's all a matter of trade-offs of what are we going to do and which one is cheaper. And so since we're doing a queue where our only operations are adding to the back and removing from the front, then all I need to do is just add front or remove front, add back, and then we're good to go, which for a linked list is instant, free, easy. Okay, so for NQ, basically what I just said. So for NQ, we want, if this is the front of the list and this is the back of the list, for NQ, we add to the back of the list. And so we do that with add last. And then for DQ, which one do we do? Remove first or last? We're in a queue now, though. So if we were in a stack, then I would say last, yes. But if we're in a queue, where you get in the back of the line, then you leave from the front of the line. So we would want to do remove first. And then maybe if the list is empty, then try to DQ empty queue. And then I just import that. Okay. Yeah.
Try to DQ empty. Does it say something like that?
Oh, I said queue.
Oh.
Basically the same thing as I said it's at the stack. It's just we're in queue land now. Other questions?
For boolean is empty, we also do return with it's empty.
Yeah, so list dot is empty. Let's say make empty. Let's see what list has. List has clear, which removes all the elements in the list. The list will be empty after this call returns. That seems the most likely. So I'll just do list dot clear. And so similarly, if we want to go and use this queue, we cannot, iterate through the queue to say, oh, who's the fifth person in line? From the outside, we only see who's at the back of the line. We can only add someone to the back of the line. We can only remove someone from the front of the line. Those are the only things we can do. Everything else, it's like it's in a black box where we can't see inside of it. We can't grab the fourth person in line and take them out. We can only add someone to the back of the line and only remove someone from the front of the line. Okay, any questions?
Is the make empty also one to
The AL stack and LL stack? Yeah, something like that. So I think for the AL stack, it'll be the same thing because it probably has the same method names. I think LL stack has the method make empty. So I think you would call that instead of clear.
what?
So for LL, if we were doing this for LL stack, I think it doesn't have the clear method, but I believe it has the make empty method. Okay, so we've got 20 minutes. So did we talk about this already? Okay. So I just want to tell you that there are some variations for things that queues can do. So one of the things like that your CPU might do under the hood is we want to be able to schedule things, and there's a fixed size of spaces that we want to be able to schedule. And so let me move this down here. So what we can do in those cases is if we typically have like a flat queue, what we could do is we could bend it and like glue the ends together. And so that makes a circular queue where like in this queue, there's 8 spots, 0 through 7. So we just glued 7 and 8 or 7 and 0 together. And so then as you go, you just need to keep track of like where's the front and where's the back of the queue, because like it may not always be at 7. So yeah, as you go, it can change. And that's used for something like CPU scheduling. And it has fixed size so that you can't like for our implementation, since we're using those underlying data structures, we don't care about adding more size, but in this case, the size would be fixed. There's also something called a priority queue, which is where there's some things that need to be dequeued first. And so this happens not only in like your operating system, where some things like updating the clock has to happen like every second, or some things have higher priority in order to keep your computer running. And so that's why if you're maybe doing something super intensive in one program, the other programs are slower because you're prioritizing this one. And so that's where we get this notion of a priority queue. And an example of this is like if you go to a hospital. So if you maybe like broke a finger or something, you would have less priority than someone who comes in with like chest pain, where that's the thing, like when you go to the hospital, if you're imminently at risk, then you move to the front of the line and the other people have to wait. And so this is a priority queue where we still have this notion of first come, first serve, but there's an additional notion of some people get to cut in line and some people get to be dequeued first.
Because if they don't, they wouldn't really go, because they wouldn't be going to die if they don't.
Yeah. So the hospital analogy makes this fairly easier to understand. And so this is an example where something like having a linked list or something can make, so if each of these boxes is like a node, then we can store not only the data, but also store some priority. And so if we have this data like A has priority 1 and C has priority 3, then when we go to NQ B with priority 2, it doesn't go here. Like it doesn't go after C because it's got higher priority than C. So it goes here instead, in between the two. And then if this is our queue, and then we go to DQ, then we just DQ the thing with the highest priority. Okay, so that's priority queue. Now we've got 15 minutes. So let's look at lab 7. All right, give me just a second. Okay, I think we should be good to go. So I just updated the class path. So the goal for this lab is we're going to use stacks and you're going to implement some advanced operations when it comes to stacks. So for both stacks and queues. So for stacks, there's a file min-max stack, and so there's two methods, min and max. And so you write methods to figure out what's the minimum thing in the stack and what's the maximum thing in the stack. And keep in mind that you can only use stack operations. So there's no iterating through it. We can only use push, pop, and peek. So once we're limited to those operations, how do we find out what's the smallest thing in our stack? I will also note when you finish finding it, the original stack should not have changed. So make sure that you somehow copy it as you go, or maybe have a secondary stack and then put things on there and then put it all back when you're done. So min and max, once you do one, the other should be easy. Probably just like flipping an inequality. For reverse queue is instead of finding the minimum or maximum, is you've got some queue and you want to reverse everything in it. And additionally, so there's NQ, DQ, those are the only operations you can use. I also have added peek front, so what's at the front, and peek back for what's at the back, if you want. Yeah, and then there's an additional requirement for a text file to talk with your partner and see what are some real world applications for these data structures. So where do you see them in real life? I have not assigned the partners yet, but I will right now. All right, I think that's it for today. Thank you for coming, and I will see you on Thursday for recursion. Please come on Thursday for recursion.